buffer system is the new subtopic. So in this subtopic, we look at to the definition of the buffer system itself, and then we look at to the common ion effect, and then we have to be able to determine the pH of the buffer solution by using Henderson-Hasselbalch equation. Okay, and lastly, we have to be able to determine the pH of the buffer solution after we add strong acid or strong base. Okay, look at to the solution in a beaker. Okay, this is unbuffered solution. Okay, when we measure the pH of this solution, then we observe that the pH is 5. And then after the addition of small amount of the strong acid, okay, then suddenly the pH of this solution that was added by the strong acid dropped to 2. The same buffer solution was added with a small amount of a strong base, then suddenly the pH increased to 12. So this is what will be happen to a solution when it is added to small amount of the strong acid and small amount of a strong base. However, if we have a buffer solution like this solution with the same pH as this one, okay, which is 5, but this solution is a buffer solution, during an addition of a small amount of acid, the pH dropped only by 0.02 from 5 to 4.98. And for the same buffer solution, when it is added with a small amount of the strong base, and then the pH increase, of course, but only increased by 0.2. So from 5 it is increased to 5.02. Okay, they are being added with the same amount, with the same acid and base. However, look at to the difference, what is happened to the pH of the solution. So buffer is actually a mixture of a weak acid or weak base with its salt. So if it is acidic buffer, so we will have a weak acid and its salt. Example of the acidic buffer, when we have CH3COOH mixed with CH3COONA. Okay, so we have a weak acid and its salt. Or a buffer also can be a basic buffer. So example of the basic buffer, when we have a weak base NH3 and its salt NH4Cl. When we have these two in the same container, then we say that we have a basic buffer. But when we have a mixture of the weak acid and its salts, we say that we have acidic buffer. And this buffer system, both either acidic or basic, okay, has the ability to resist the pH changes upon the addition of a small amount of a strong acid and strong base. So that is the buffer system. Then let's look at the common ion. If we have a solution with two dissolved solutes that contain the same ion, we said that solution contain common ion. For example, when we have a solution of the acetic acid and sodium acetate, they have the common ion of acetate, CH3COO minus, CH3COO minus. And then the common ion effect, okay, is the presence of the ion in common, the same ion that is present, cause a shift in the equilibrium. Okay, it's either it suppresses the dissociation of acid, okay, base making it to be less acidic or less basic. Okay, so let's consider if we have a sodium acetate and acetic acid that is dissolved in a beaker. So when we have a mixture of these two, means that we have acidic buffer. Okay, so in the same container here, we have acetic acid and sodium acetate. The common ion, as I said just now, is acetate ion. Okay, it is because acetic acid undergo dissociation or hydrolysis, it will form acetate ion and H3O+. While sodium acetate, the salts, during the dissociation of these salts, it will form Na+ and acetate ion. So we have this acetate as a common ion in our system. So according to the Le-Chatelier principle, the common ion suppress the dissociation of the acetic acid and making it to be less acidic. Okay, when we have acetic acid that is added by sodium acetate, means that we are adding more acetate ion into the system. So the acetate concentration increase. So when the acetate concentration increase, the system will shift to the left to consume extra acetate ion. Therefore, the system will produce more acetic acid. Okay, so that it is less acidic because the H3O+ concentration will be decreased as well when the system shift to the left. Okay. So the same example as before, when we have acidic buffer, we have a mixture of the acetic acid and sodium acetate. So actually in the system we have acetic acid, acetate, H3O+. Okay, these are the components of the acetic acid. And then from sodium acetate we have acetate ion and Na+. So these two in common. So if you want to determine or to calculate the pH of the buffer system, okay, we can use this equation. Okay, so if we have acidic system, pH is equal to pKa plus log concentration of the conjugate base or concentration of the salt over concentration of the weak acid. While for the pOH, it is equal to pKb plus log concentration of the salts over the concentration of the weak base. So how the buffer system works? So let's consider that we have sodium acetate and also acetic acid. The mixture of these two makes we have a buffer system here. Okay, so when HCl is added to this buffer system, we know that what is being added to the system is an acid or H3O+, which is the same as the H+ ion. Okay, so when acid is being added to the system, it will be reacted with the base. So we have acetic acid and acetate ion. We know that acetate ion is a conjugate base. Okay, so that HCl that's being added to this system is actually reacted with the acetate ion. So when we write the equation upon the addition of the HCl, it is actually the H+ that is reacted with the acetate in the system, and it will produce acetic acid. So during the addition of the acid, okay, the concentration of the acetate will be decreased as it is reacted with the added H+. The concentration of the acetic acid will increase because it is produced. And what if we adding a base? So when base is being added to a buffer system, so base will be reacted with the acid in the system. So the acid in the system is actually acetic acid. So sodium hydroxide base is actually hydroxide ion that is reacted with the acid in the system, which is CH3COOH, and it will produce acetate ion plus H2O. So since the hydroxide that is being added need to be reacted with the acetic acid, so the concentration of the acetic acid will decrease and it produces acetate, so the concentration of the acetate ion will increase. That's what happened during the addition of the small amount of the acid and base in a buffer system. And the most effective buffer is when the concentration of both components are equal. When the concentration of the salts and also the concentration of the weak acid is equal, or when the concentration of the salts and weak base are equal. It is because during this time the pH will equal to the pKa value. Remember pKa means negative log Ka, acid dissociation constant. And then if we have a basic salt, it will be POH equal to pKb. Okay, so this is for the acidic, this is for basic. This figure is also showing us on how the buffer system is working. So if you look at to the system that we have, okay, in the system we have acetate ion and acetic acid. So we know that this is the buffer system when it consists of the CH3 COOH and also its salt CH3 COONA. So we know that when we have this buffer system, in the system we have acetic acid, and then for the salt we are actually having acetate and Na plus. Okay, and then in the buffer system we have to identify what is the acid and what is the base in the system. So in this case our acid is the acetic acid and the base is the acetate ion. This is our conjugate base. How do we know that this is our base? Because in the acetic acid dissociation reaction, it will produce acetate ion and also H3O plus. So acetic acid is the weak acid, so acetate ion is the strong conjugate base. Acid, base. Okay, so in this buffer system, when we look at to the concentration, they are the same between acetate and acetic acid. What is happen when a small amount of the acid is added to the system is actually H3O plus ion that being added. We have to decide, okay, in the system the addition of the acid will react with the acetate or it is reacted with the acetic acid. So since the acid is being added, so it will be reacted with the base. So in this system our base is acetate ion. So when the H3O plus from acid is reacted with the acetate ion, the equation will be acetate plus H3O plus or produce acetic acid and H2O. Okay, if we refer back to this equation, when H3O plus is added, okay, means that at this side H3O plus is added, so acetate ion will decrease to be reacted with the addition of the H3O plus, and the reaction will shift to the side that is producing CH3COOH and H2O. So when the H3O plus is added, acetate ion will decrease, the reaction shift to the left so that it will produce extra acetic acid. Okay, so acetate decrease, acetic acid increase. And what is happen if the base that is added to the buffer system. So when base is being added to the buffer system, we are actually adding hydroxide ion. So we have to decide when the hydroxide ion is being added, it will be reacted with the acetate ion or acetic acid. So since that hydroxide is a base, it will be reacted with the acetic acid. Okay, so the equation will be acid reacted with the hydroxide ion, then it will produce acetate ion plus H2O. Okay, so acetic acid's concentration will decrease to be reacted with the addition of the hydroxide. Concentration of the acetate will increase. So this is our acid and this is the salt's concentration. Okay, so how to calculate the pH of the buffer system? Okay, without the addition of the acid, base, okay, and after the addition of both acid and base. Okay, in this sample problem, okay, we have 0.5 molar of the acetic acid and 0.5 molar of the sodium acetate. We have to calculate the pH of this buffer system. So when we know that we have a buffer system, we can strictly using the equation pH is equal to pKa plus log concentration of the salt over concentration of the acid. Okay, we know that there are two Henderson-Hasselbalch equation, either pH or pOH. So this time I'm using pH equal to pKa is because of this system is acidic buffer system. Okay, so if we have a basic buffer system, then we use the equation pOH equal to pKb plus log concentration of the salts over base. Okay, so we can plug in the value. pKa is negative log Ka value that is given is 1.8 times 10 negative 5 plus log concentration of the salts is 0.5 molar over concentration of the acid 0.5 molar. So when we press the calculator, then we'll get the answer is equal to 4.74. As for B, calculate the pH after the addition of 0.02 mole of the solid sodium hydroxide to 1 liter of the buffer solution. So base is being added, so we have to decide in the system, okay, what is our acid and what is the base. So we have CH3 COOH plus with the H2O dissociate into CH3 COO minus plus H3O plus. So acetic acid, of course it is an acid. During dissociation, this is its conjugate pair, so this is the base. Okay, weak acid, strong conjugate, base. Okay, so when sodium hydroxide is added, it will be reacted with the acid because sodium hydroxide is a base. So we write the equations of a reaction. So this time we have to construct the reaction table, almost the same as the ice table. Okay. And then in our reaction table, we have a reaction of the acetic acid that is reacted with the OH minus that being added, it turns to CH3COO minus and H2O. So acid-base reaction will produce a salt and H2O. So an initial amount of the acetic acid is MV, which is equal to 0.5 molar multiply with 1 liter. So the initial amount is 0.5 mole. Hydroxide that is being added is 0.02 mole. Acetate ion that come from our sodium acetate is 0.5 multiply with 1 liter is equal to 0.5 mole H2O dash. Then mole change is minus 0.02 minus 0.02 plus 0.02. Okay, why plus and minus 0.02? It is because the amount of the hydroxide that is being added is 0.02 mole, so it will react with acetic acid with the same amount. Okay, because their ratio is 1 to 1, so 0.02 will require 0.02 mole of the acetic acid, and it will produce 0.02 extra acetate ion. Then we have amount final, so 0.5 minus 0.02 is equal to 0.48. This is 0 and 0.52 dash. So this is the new amount of the acetic acid and also sodium acetate. Then we can calculate the pH by using the same equation as before. So identify which one is the acid and which one is our salt. So this is our acid, new amount, this is salt. Okay. Then the question 1, the concentration final, so that 0.48 divide with the volume, which is 1 liter. So the concentration is also the same as the number of mole. Same goes with the concentration final of the sodium acetate is 0.52 molar as well. So plug into the equation. pKa negative log 1.8 times 10 negative 5 plus log salt is 0.52 over 0.48. Then we just press the calculator, then we'll get the answer 4.77. Let's look at to the question C. What is the pH after the addition of 0.02 mole of the HCl to 1 liter of the buffer solution? So when HCl is added, we know that what is being added to the system is actually H3O plus ion or H plus. So when H plus is added to the system, this H plus is actually will be reacted with the acetate ion. Okay, because H3O plus is acid, acetate is the base. So we have to construct the reaction table. So the reaction table will be acetate reacted with the H3O plus being added from the acid of HCl. Then it turns to CH3COO H plus H2O. So initial amount acetate ion is 0.5 mole, which is the same as the concentration because it is in 1 liter solution. H3O plus that is being added is 0.02 mole. Initial concentration of the acetic acid, okay, from the buffer system is 0.5 mole dash for H2O. So the amount that is changed is minus 0.02, which is the same amount of the H3O plus that is being added because their ratio is 1 to 1, and for the acetic acid plus 0.02. So the amount final will be 0.48, 0.52. Concentration final will be 0.48 over 1 liter, 0.52 over 1 liter. So it is equal to 0.48, 0.52. So to calculate the pH, identify acetate is our salt and this is our acid. So just plug in the value in our equation. So this equation pKa negative log 1.8 times 10 negative 5 plus log concentration of the acid is 0.52 over 0.48. Then press the calculator. Then we'll get the new pH is 4.71. So if you look at to this question, we have completely calculate the pH of the buffer system before the addition of any acid and base, and then we have calculate the pH after we add solid of the sodium hydroxide and solid of the HCl, in which this question we have to assume that the addition cause a negligible volume changes. In other question, sometimes the base and acid that is being added to the buffer system are in a solution form, so that we have to calculate the final concentration by considering the new volume after the volume of the buffer system is being added with the volume of the sodium hydroxide and HCl that is added. So for this question, okay, it is more simple, okay, but please answer your follow-up problem in the textbook to experience more type of the question.